All right, so we already have the discussion about random variable and properties. That's correct, right? Because you will feel how to have those properties. And keep in mind those properties. Last time for the exercise, I will already have for the exercise, but no need to hand in. 我会给你作业，但作业不用交。Programming assignment 是 programming assignment， 我不称交作业。All right, so I will already have for the exercise, taking some problem from, for example of chapter 4. Then you can practice. So how to have the solution? Sometimes you need to use properties here, right? Well, with this one ready, and of course I will already have the solution approximately a week later. Well, that is about these random variable and properties. Any questions? If no, let me go to the next one, simulation output and stochastic process. In fact, simulation output data, they are random. Sure, then you can accept these because we have input random variable, right? Because of a random variable, so we already have this. Have care in drawing conclusions because of a random variable. It doesn't mean we have the fixed value. Well, this is the first one. Simulation output. All right, output data, they are random. And if we want to talk about simulation, in fact, we can rely on the process called stochastic process. To define stochastic process, it will be this collection of similar random variables. And because of time, so we can alter over time. And so that you have time instant one to have a random variable, but similar random variable. Time 2, you have random variable 2. Follow, for example, the same distribution. And another time instant, you can have a different similar random variable. If so, we can get them together so that we have the collection. And this collection we can call, we have the stochastic process. Well, up to now, about simulation output and stochastic process, is it okay? Well, if it is okay, we can check next one. Yes, we have a simulation model and model. Actually, the output will be random, and the stochastic process actually collection of a similar random variable. Well, again, we can have a discrete and continuous. If we have a finite or countably infinite random variable, then we call discrete random process. And likewise, we have continuous stochastic process. All right, so finite or countably infinite random variable collection, this collection. Or otherwise, this collection should be continuous stochastic process. Well, again, we have these, but right now we talk about stochastic process. Well, this is example. Put them together to consider the output. So we consider MN1. MN1 in the past we have ID turnaround times and also ID service times. And we use first in, first out. So up to now, we just describe MN1 to let it know. And in fact, you can define by define delays. Here we have a delay. It says, is it okay to find delay? Here delay means during delay. The first customer during delay 0. The second delay, third delay, and etc. If we can use simulation to have delay. And here, why it is called, I'll just ask you, why we can have this to have discrete time because 1, 2, 3, of course, we can have the countably infinite delay. So of course, we have the discrete time stochastic process. So look at this. Simulation output are random. Because of random, we can use stochastic process to know the behavior of the queuing debates. That's all. So there you have the terminologies. Simulation output are random variables. And actually, it should be the collection of a random variable. Because of a collection of a random variable, so we can use principle of a stochastic process to study these outputs. Well, this example just want to practice terminology we defined before this example. Is it okay? If it is okay, then we can have the next one. We can use discrete time, right? So up to now, for that example, M1 output, we can define stochastic process. Discrete time stochastic process. However, if we consider stochastic process, we have a really broad range. Because we want to have some cases. Cases should for us to study. So we have this specific stochastic process, covariance stationary. Well, this is a definition. Definition of covariance stationary. How to define definition of covariance stationary? Mu, the same. Variance, the same. Right, so first of all, we have these. As for covariance, independent. If so, then we have a covariance stationary. So covariance stationary, we talk about covariance here, independent, but we have a same mean and same variance. If you don't like covariance, you can use correlation. All right, so well, up now you feel well. It's really direct to have the result. Covariance stationary. We have mean and variance the same. In fact, it should be finite mean and finite covariance. And finite mean and finite variance. As for covariance, covariance are independent of I, the initial position. Well, it's just a definition, and no further problem, I think. So you can check the definition. What that means, covariance stationary.